The A1601 glider project tasked students to create a glider out of balsa wood that could fly at least 20 feet and fit in a square that was 16 by 16 inches. During creation, the student should pass 2 checkpoints where the design choices are analyzed and backed up by the student. In the ideation of my design, I found the dihedral or elliptical plan forms to have the highest chance of success. In class, Dr. Patil had noted that the dihedral plan form had a high stability due to its self-correcting properties. However, the trade-off to the dihedral plan form is that they are hard to make out of balsa wood. While the creation of the upward sloped wings is possible, the chances of the project breaking is much higher in the creation of the plan form that must be bent. Unfortunately, the elliptical plan form does not have the self-correcting properties of the dihedral plan form. However, from the online research I was able to find, is that elliptical plan forms are seen to be more efficient than a straight or taper design, and that includes the dihedral design. This is because the elliptical wing plane has the lowest amount of induced drag compared to all other planforms. Further, elliptical planforms are much easier to manufacture than dihedral planforms, as a simple laser cut is all that is needed to make the elliptical planform, compared to bending the wings a little bit each day for the dihedral, where you have to worry about the wood breaking if you mess up. In the design process of the stabilizers, I wanted to keep my design consistent throughout, so I made the horizontal stabilizers elliptical as well. This way, the main plane form would only need to be scaled down before cutting, opposed to calculating the area of another shape to get the ideal ratio between the two. The other shape I considered in the design was the T-shaped horizontal stabilizer, as this is seen in the Boeing 717 and 727, because this design is seen to have better pitch control. However, I decided against it because previous designs with the stabilizer were shown to be more fragile because the T-shaped stabilizer would break off very easily. The glider was longitudinally stable because the center of mass was placed in front of the center of lift. This was done through placing the provided Play-Doh on the nose of the glider until the center of mass was about at the quarter chord of the planform from the leading edge. The center of mass for my glider was about at the quarter chord because I marked where the quarter chord was considering my average chord length of my elliptical planform, which was about 2.4 inches, and tried to balance the glider on my finger at that spot so that I could tell if the weight was distributed behind or in front of that point. I kept testing until different amounts of Play-Doh until I could balance the glider on that spot. The lift coefficient is 1.8 times 10 to the negative 6, and the drag coefficient is 3.6 times 10 to the negative 13. I estimated these values by weighing my glider, measuring its average velocity through test flights, and measuring its planeform area and wingspan to input into the equation for the lift coefficient. I then used those values to find my induced drag coefficient. I added the induced drag coefficient and the zero lift drag coefficient that was assumed to be equal to the induced drag coefficient to find my overall drag coefficient. I only made one prototype, and I started my prototype with a straight planeform because I was a little lost at the beginning of the project. I was unsure how to tell what the best planeform, center mass, and stabilizers were. However, after further research and analysis of other balsa gliders online, I got the essential knowledge for making a glider that would meet the requirements of the project and at least fly 20 feet. The initial design went pretty well, and a straight planeform definitely could satisfy the requirements of the project. However, I could see based on gliders online that the straight planeform was rarely used, as it is not the most efficient considering the amount of drag it induces compared to the lift it generates. With this in mind, I considered the most common designs were dihedral, elliptical, and swept-back, and I began to choose between the three. I ended up picking the elliptical planeform as my main change because it was the easiest to manufacture of the three options, such that I wouldn't break my glider, and I could have a strong planeform because I had to make it as one piece. Along with that, I found that the elliptical glider was able to fly longer when I tested it, likely due to the little drag it induces compared to the lift it generates. My glider broke in the process of testing and retesting after the final throw, so here's an image of my CAD model with the exact dimensions of my real-life glider. This glider clearly fits inside the 16 by 16 requirement, as the wingspan is 14 inches long and the fuselage is 8.5 inches long. In terms of final thoughts, this project challenged me to create designs with a level of uncertainty. While I could make reasonable claims about my design, I had no idea if it was the best or could be improved. This improved my ability to design through educated prototyping and not known facts. If I were to do the project over again, I would change the angle of the planeform to about 5 degrees from the fuselage to generate more lift. I wasn't confident enough in my laser cutting abilities to do this design during the manufacturing of my glider. But after practicing through the assignment, I feel confident that I could laser cut a 5-degree angled slot in my fuselage next time.